Hey guys, welcome to video 84. Today we're going to continue along the lines of the previous video where we talked about the distortion characteristics of BJTs, FETs, and triodes, and we're going to extend that to the concept of the transfer function. We've seen this in some form or another in many previous discussions, but in general the transfer function of a system is just the ratio of its output to its input. And some of the simpler versions of this that we've dealt with many times are voltage gain, current gain, power gain, and transconductance, just to name a few. But in general, transfer functions can be pretty messy things. They could be ratios of functions of time, functions of frequency, or even functions of complex frequency, which is something we'll talk about in the future. Now, let's just take a look at some notation you're likely to see when you're dealing with transfer functions. The first one listed here, h of j omega, we've seen this before when we talked about filters and decibels. It's just the total response of the filter, amplitude and phase. We can take the magnitude of that, which just gives us the amplitude response. H of f would be similar to the magnitude of the response, just expressed in terms of hertz instead of radians per second. AV of f would be the voltage gain as a function of frequency, typically what we would see in a Bode plot. And these last three, T of s, X of s, Y of s, these represent functions of complex frequency where S is sigma plus j omega. This is something we deal with if we're analyzing circuits using Laplace transforms. And we'll talk about this in future videos, but not for a while, so don't worry about it. It's just something you may see, and this is what it means. Now, coming over to the right-hand side, we've got the symbol for a voltage amplifier shown here, and its transfer function is a graph of the output voltage versus input voltage. We'll assume it's a non-inverting amplifier, and if it's a real amplifier, we know it's going to clip at VO max and VO min, but between these two limits, it should behave linearly, and the slope of the line connecting these two limits is the voltage gain of the amplifier. Now, of course, we know that amplifiers don't always behave linearly. We've seen that many times. And if we drive an amplifier into clipping, it certainly is going to be nonlinear. And that's what this video is mostly going to be about, how to determine what kind of frequency components you're going to generate in your output when we do hit clipping or we have nonlinearity in between these two limits. Alright, so now that we've got some of the basic terminology out of the way, let's go on over to the next page, and I want to talk about functions and symmetry. One of the primary characteristics of a function is its symmetry. Now, we can have either even symmetry, odd symmetry, or something in between, which is neither even nor odd. If we start with even functions or functions with even symmetry, that just means that the function has symmetry about the vertical axis. Technically, it means f of negative t equals f of t. All right, now that's a little hard to relate to sometimes, so a way to think about it is if we have an even function like a cosine waveform, if we place a mirror right here on the vertical axis and we reflect that waveform on the mirror and look at its image, it's a perfect continuation of the function as we have shown here. Now, odd functions have symmetry about the origin. That means f of negative t equals negative f of t, which again is something maybe hard to visualize. So if we use the mirror approach here with the sine wave, which is an odd function, we see that its reflection is an inverted version of what would really happen for negative t. And this is just a visual way of seeing what's going on with this equation. And hopefully the mirror approach I've used here helps you to be able to visualize even and odd functions a little more easily. And this takes us over to our final case where we've got a function that's neither even nor odd. A good example is this decaying exponential shown here. And if you wanted to, you could decompose this into even and odd parts using these formulas. And I'm going to give that as an assignment right now. I'd like you to take this equation and figure out the even and odd parts of this function, and I'll present the answer at the end of the video, but just apply these formulas and see what you come up with, and we'll go from there. What we're going to do next is go on over and take a look at some functions with various types of symmetry. Starting on the left here, we've got a cosine waveform, which we've already looked at. We've got a simple quadratic that gives us a parabola for its graph, and down at the bottom we've got a rectangular pulse train with even symmetry. This one is shifted above zero with a DC offset, but it's still an even function. Now coming over to the middle, we've got some odd functions, the sine wave, a cubic equation, and down at the bottom we have another square wave. This one does not have a DC offset, and it's got odd symmetry, very similar to the sine function. Then finally we've got functions that are neither even nor odd. Again, the decaying exponential, a random voltage here that just fluctuates all over the place, and a swept sinusoid. Now at this point, a fair question you might be asking is, well, how does this relate to distortion and amplifiers and the things we've been talking about? And that's what we're going to look at next. So let's go on over and let's assume that we'll start with an input voltage that's a sine wave, that is Vn equals Vp sine omega t, and we're going to look at the circuit in terms of the frequency domain. So our input signal is just a spike here at Fn hertz with an amplitude of Vp volts. If we apply this input to a system that has an even transfer function and it's nonlinear, then the output should contain only even harmonics of the original input. So on our output we should see 2Fn, 4Fn, 6Fn, and so on, and possibly a DC component at 0 times Fn. Because remember, 0 is an even number, so that counts as an even harmonic of our input signal, no matter what the frequency is. If we apply this same input to an amplifier that has odd transfer function symmetry and it's nonlinear, the output should only contain odd harmonics, and that means it should contain the original frequency. 1 is an odd number, so 1 times Fn comes out, then 3, 5, 7, and so on. And generally speaking, the harmonics are going to diminish in amplitude as we increase in frequency. And that's the same with the even transfer function symmetry as well. Now, in the case of an amplifier with a transfer function that's neither even nor odd, because we can decompose this into even and odd parts, we're going to have some characteristics of both functions. So when we apply our input, we're going to get both even and odd harmonics on the output, and again, possibly a DC component as well. Now, so far this discussion's been pretty abstract, so let's bring it a little bit more down to earth by looking at an actual circuit. We'll start with a circuit that we're all pretty familiar with. That's the basic BJT push-pull output stage. Remember, this circuit exhibits a lot of distortion right off the bat because we have to overcome the barrier potentials of the transistor base emitter junctions to get anything out, and we call this crossover distortion. Now, if we come over and look at the transfer function, we see it does have odd symmetry. It's symmetrical about the origin. And we've got a couple of different kinds of distortion or sources of distortion occurring here. We've got a discontinuity here when we exceed VBE for each transistor, and we also have a discontinuity, that is a change in the slope of the transfer function, when we go into saturation on positive and negative going output swings. Coming over here to look at what's going on in the frequency domain, our input sine wave has one frequency Fn at some particular amplitude, and the resulting output is going to consist of the original frequency plus odd harmonics 3, 5, 7, and so on. Now, I did a PSpice simulation of this circuit, so let's go on over and take a look at that. Here's our circuit in the schematic editor. I used plus or minus 10 volts for my supply rails, and I put in a sine wave that was 2 volts peak with a frequency of 1 kilohertz, and it gave us this output signal. No surprise here. The spectrum for this output is shown below. We've got the fundamental at 1 kilohertz and odd harmonics out to about 7 kilohertz. Anything beyond that is too small to see. Now let's take a look at another example of a circuit with odd transfer function symmetry. The circuit we've got here is pretty typical of what you'd use to implement a distortion effect. We have an inverting op-amp with a gain of -1 and is driving a diode clipper that limits the output voltage to about plus or minus 0.7 volts. Now, we haven't talked about op-amp circuits yet in this video series, but we'll get there soon enough. But in any case, if we apply a sine wave input with an amplitude of 2 volts peak, this is what we'll get on the output. And the transfer function for our circuit looks like this. It is an odd function. We've got symmetry about the origin. So we would expect the output to contain only odd harmonics, and running through a PSpice simulation, I posted the FFT of the output signal here, and we can see we do get the original fundamental on the output plus 3, 5, 7, and about up past 9 kilohertz. We don't really see much of anything, so we are getting the odd harmonics in the output as we would expect. Now let's go on over and take a look at a circuit that has a transfer function with neither even nor odd symmetry. This is a fully bypassed Class A common emitter amplifier. We looked at it back in video 53, and it had a gain of about -135. Its transfer function is shown down here. And based on the analysis we did, this -135 gain would be the slope of our transfer function here at the origin. Now, as the output goes positive, the voltage gain decreases, and when the output voltage goes negative, the voltage gain increases, and that's what accounted for this squashing and stretching on the output waveform that we see here in the scope capture. Now, the spectrum for the output signal is shown below, and we can see it does contain the original fundamental plus the second harmonic, third harmonic, fourth, fifth, and so on, and there's not a real nice relationship between the amplitudes. We can see the third harmonic is a little smaller than the fourth, but we are getting both even and odd harmonics as we would expect from a transfer function that is neither even nor odd. This behavior is pretty typical of what we'd expect for any Class A amplifier, whether it was a BJT, a field effect transistor, or a vacuum tube. And this is one of the reasons why amplifiers sound so different when they're driven into distortion via their input preamp stages, which are typically Class A, versus distortion when the output push-pull stage is overdriven, which is typically Class B or Class AB. The Class A amplifiers, when they're overdriven, produce both even and odd harmonics. The Class B or AB output stage typically produces only odd order harmonics when it's overdriven. Okay, we're going to talk about circuits that have even transfer function symmetry next, but before we do that, I'd like you to pause the video and see if you can think of a circuit that has an even transfer function. Okay, let's go on over and take a look. About the only thing I can come up with that has this characteristic is the absolute value function, or a full wave rectifier, which is very closely related. Now, the transfer function for the absolute value is shown here, and as you can see, it does have even symmetry, as does the full wave rectifier, although it has this little dead band down here as well. But over here I've got a PSpice representation for the absolute value function, and if we apply an input sine wave 10 sine 2 pi 1000 t volts, this is the output that we get, and of course it looks like a full wave rectified sinusoid that we've seen many times before. And the spectrum for that signal is shown down below. We've got a large DC component, which we expect to get. It's the 0th harmonic. We also have 2 kilohertz, 4 kilohertz, 6, 8, and so on. So we are only getting the even harmonics on our output. So a circuit with an even transfer function would not make a good amplifier, but it does serve well as a full wave rectifier, and there are other applications as well. And by the way, we'll look at various precision rectifier circuits later on in the series 2, where we can get rid of this dead band and more closely approximate the absolute value function that we have shown here. So that just about wraps it up for today's video. Hopefully this gave you a little bit more insight into how transfer function shape and characteristics can affect the distortion of an amplifier. We're going to talk a lot more about this stuff later when we get into the design of effects circuits. But for now, I'm going to leave you with the derivation of the even and odd parts of the original decaying exponential we looked at the beginning of the video. And how we come up with these even and odd parts is by substituting this function into the definition for the even parts and odd parts that we looked at earlier, and it gives us what's called the hyperbolic cosine for the even part. Sometimes it's pronounced the cosh of alpha t, and the negative hyperbolic sine of alpha t, which is also sometimes pronounced sinh of alpha t, as we have shown over here. And if we add these two together, we end up with the original function. So there you go. And that's it for today. I'll see you guys next time around.